Last time, we made a plausibility argument for the Schrodinger equation, which, as I said, is going to be an equation that we use throughout this course in quantum mechanics. There are other ways of arriving at the Schrodinger equation and other ways to develop quantum mechanics. One of the really intriguing ways to do so is to use a linear algebra approach. And so what I wanted to have from the first couple of lectures was something to sort of work towards, that is to say the Schrodinger equation. But what I also want is a completely different development, a way of making you think of quantum mechanics as not being anything like what you've done before. And I think that's important because in some ways, while we had to have a classical jumping off point, it still should be emphasized that quantum mechanics is very, very different. And so to take that approach, we're going to use this notion of an idea that we talked about quite a bit last semester, which was spin. Plenty of examples of spin in statistical mechanics, lots of two-state systems. So what I want to do now is to bring spin into the argument. In fact, we're going to bring in spin and nothing else. We know that particles have spin in addition to having an orientation in space. It's a completely non-classical concept. The particle itself isn't spinning. That's just a word we use to describe this degree of freedom. But for the moment, let's divorce spin from all particles. Let's just look at spin for spin's sake. Don't worry about whether we have a photon or electron or neutron, proton, whatever. We're just going to worry about the spin itself. Quantum systems, quantum spin, is an example of a class of system that are called qubits, or quantum bits. They're analogous to logical bits that sort of define the state of your computer and other classical systems. Well, in conjunction with spin, we're going to invent a degree of freedom. And we're going to call this degree of freedom sigma. And we're going to allow sigma to take on two values, either +1 or -1. Nothing else. So a system can be in either a +1 state or a -1 state. We're not going to worry about the nature of the system other than that. But as you see, going back to our statistical mechanics ideas, it's a two-state system, +1 or -1, heads or tails, so on and so forth. So in a really simple experiment, we can think of a system that has an apparatus and then a system that creates a spin. So as in our statistical mechanics class last semester, let's orient the apparatus in the z direction. And if the spin is +1, it points in the same direction as z. If the spin is -1, it points in the opposite direction as z. Very simple. Ahead of time, we have no idea whether the spin is going to be up or down, or +1 or -1. That's before we make a measurement. So it may be that once we make a measurement, if the spin is up, the results window will give us a +1. If the spin is down, it'll give us a -1. So it's blank until we do the experiment, and then it's either +1 or -1 after we do the experiment. Now, let's just say we run the experiment, put our system into the machine, and it reads +1. And we do the experiment again. Again, it reads +1. And again, and again, and again, and again. So we're confirming that the state is +1. Okay. Now suppose we turn the apparatus completely upside down. Now, of course, we expect to see -1. Sure enough, that's what happens. And as long as I keep my apparatus upside down and do the same experiment over and over and over again, I'm going to get the same -1 as an answer. So you might be thinking, this must have something to do with how I orient my apparatus. Like in space, if it's pointing in one direction, I get a +1. If I put it in completely the opposite direction, I get a -1. Let's see if that's really true, though. If spin is a vector, the way we think of three-dimensional vectors, we would think that it would have three components: sigma x, sigma y, and sigma z. And of course, what we were measuring in the first experiment is sigma z. It's upright, we're measuring plus z and so on. But suppose I rotate my apparatus. Instead of in the z direction, now it's in the x direction. So that's the z direction, here's the x direction. Now what I would expect to see then is that if I rotate it at 90 degrees, if this has really got to do with orientation, every time I make a measurement, I should get 0. Because when I use the apparatus in the +z orientation, if it were going along with z, it was going to be +1. If it was going against that direction, it was -1. Here it's 90 degrees away. And we would think that the component, or if you will, the dot product, would give us a 0. But we would be wrong. Because our apparatus, amazingly enough, is going to give us a result that's, again, +1 or -1, regardless of what it was when we measured it in the z direction. So we think we're measuring sigma sub x, and we are. What we find, though, is that let's say we have particles that were all, or a system that's all in the plus, that is, has a sigma z equal to +1. If I send all of those, let's say many, many, many of those, into my sigma x machine, I'm going to find, on average, let's say I have a very large sample size, on average I'm going to have as many sigma x +1 as I do sigma x equal to -1, which tells me on average I'm going to get essentially 0. Interesting. So classically, we would have expected to get 0 with every single measurement. With quantum spin, we don't get 0 with any individual measurement, but if we take all of the measurements together and take an average, we get something that approaches 0. Amazing. We can modify the experiment too. Suppose we don't change it by 90 degrees. Suppose we just change it to some arbitrary angle theta. So suppose we tilt the apparatus at some angle theta, that it points in a direction that we're going to call unit vector n. Classical result would say, well, we should get sigma should be equal to cosine theta. If I orient the apparatus at theta degrees from up and down. And I take a bunch of sigma z equals 1, and I send them through the apparatus, I would think that I would get something equal to cosine theta. Once again, that doesn't happen. I either get sigma, we'll call it sigma sub n, is either equal to +1 or sigma n is equal to -1. However, again, if I take a whole bunch of experiments, if I run a whole bunch of experiments, what I'm going to find is that on the average sigma n turns out to be equal to cosine theta. Again, a departure from the classical expectation, but on average, we still get the classical result. We can look at the general case of this. Let's say I pick some direction m and start with an up arrow pointing along m, and I prepare a spin so that the apparatus reads +1. If I rotate the apparatus to direction n by some angle, once again I'm going to find that the average sigma that I get is going to be equal to n dot n, just as a follow-on to what we did before from sigma z to sigma n. Again, on average, even though any one result is still going to give me either a +1 or a -1 for the individual spin that comes through, on average, it's going to be equal to n dot n. Pretty amazing. So this is a departure from what we would expect classically, but it gets worse. Whenever I run an experiment in quantum mechanics, I have to be very cognizant of the fact that the measurement is going to be disruptive to the whole system. No matter what I do, I can't help but disrupt the system when I make a measurement. So suppose I prepare a sample with all sigma z equal to +1. And then I run that beam through a sigma x experiment. I'm going to get either +1 or -1. I'm not guaranteed to get sigma x +1 just because sigma z is +1. On the other hand, if I run that experiment and then run those particles through another sigma z apparatus, you're probably thinking, well, it was sigma z equal to 1 when it started. It should be sigma z equal to 1 now. No, that won't happen. Because by running the beam through a sigma x experiment apparatus, I've disrupted the original orientation of the spin. This is very different classically from the classical case. And in fact, it very much matters whether I run the experiment sigma z to sigma x or sigma x to sigma z. I'm going to get different results. This is extremely, extremely different than what we would expect from the classical case. So something about this doesn't smell right. Something is making us think that the vector spaces that we talked about earlier, vectors like electric field and velocity and acceleration and force and things like that, where we would talk about components in the x, y, and z directions maybe, or something of that nature. Something is not the same when I move into things like spin. There's something that's happened to the notion of what a vector space is. And that's the topic of where we want to go next. talk about vector spaces. In classical physics, we operate with Boolean logic, and the space of states is just a set of possible states. But in quantum physics, the space of states of a quantum system is not a mathematical set. It's a vector space. And relations between the elements of a vector space are different than those between elements in a set. And so are the logical properties. So what you need to do at this point is forget your preconceived notion of what a vector is. Those vectors that you knew and loved, electric field, magnetic field, force, acceleration, we now call them three vectors. Three vectors. We're not going to call them vectors. We're going to call them three. They're a special case of vector. Mathematical vector space is an abstract construction that may have nothing to do with ordinary space at all. In fact, you could have an infinite dimensional vector space. In quantum mechanics, we talk about a special type of vector space called a Hilbert space. And a Hilbert space can have a finite number of dimensions. It can also have an infinite number of dimensions, depending on what we're talking about. In quantum mechanics, we're going to talk about vector spaces being composed of kets. A ket is this sort of right-hand version of a larger word. This terminology is due to Dirac. And just to show you where it comes from, Dirac used a notion like this, where he called this side a ket, and the left side a bra, and of course you had this operator C in between, which gave you the whole word bracket. That's where the terminology comes from. And we'll talk about bras later on, but the main attraction in Hilbert space is going to be the ket. We'll call that, and we'll use A as an example of a ket. Let's talk about the properties of this vector space. So for one thing, if I take two kets and add them together, maybe to make a third ket called C, the sum of any two kets results in another ket. Also, kets are commutative under vector addition. So A plus B is equal to ket B plus ket A. So it's commutative under vector addition. It's also associative under vector addition, so that A plus ket B plus ket C is equal to A plus ket B plus ket C. Associative property. There's also a zero vector such that if I multiply A by, if I add a zero vector to A, I just get A back. And it's a unique zero vector. Also, for any ket A, I can think of a ket minus A such that if I add the two together, I get zero. Another property, if I have some complex number Z and a ket A, if I multiply Z times A inside a ket, that's equal to Z times ket A. Maybe that's equal to ket B. Also, Z times A plus ket B is equal to Z A plus Z B. And if Z and W are two complex numbers, and I multiply by a ket A, that's just like having Z times ket A plus W times ket A. So those are just some of the properties of kets in our vector spaces. Notice, already you see a departure from your old vector friends because you can't multiply three vectors by complex numbers. You can only multiply three vectors by real numbers. So already we know that kets form a complex vector space. Three vectors can only form real vector spaces. About functions and column vectors. We can represent kets by column vectors. So I can write the ket A as alpha 1, alpha 2, nice column vector, and maybe the ket B as beta 1 and beta 2. And of course, such that if I add the two, it's like adding two matrices. I'm going to get alpha 1 plus beta 1, alpha 2 plus beta 2, just as if I were to add matrices together. Also, if I multiply by a scalar, if I take Z times alpha 1, alpha 2, I'll get Z alpha 1, Z alpha 2, where again, Z is a complex number. Complex numbers have dual versions, or complex conjugates, if you will. If I have some complex number alpha, I can think of a number that's complex conjugate alpha star. It usually means turning the i's to minus i's and vice versa. Ket spaces also have dual versions. They're called bras. So if I have a ket A, its bra looks like A, turned around. Bra vectors satisfy the same axioms as ket vectors, but you have to be careful because if Z is a complex number, Z times A corresponds with A times Z star, not Z. So be very, very careful with when you go into the dual space, into the bra spaces. Since we represent kets by column vectors, we represent bras by row vectors. Alpha 1 star, alpha 2 star, alpha 3 star, alpha 4 star, alpha 5 star. So they're going to be different. We can take an inner product. We can define the notion of inner product. You've seen that before. In 3 dimensions, we called it dot product. This notion of taking a bra and a ket together, multiplied together, this will result in a complex number. Whereas in scalar product in 3 dimensions, we think of if I take A dot B, 2 vectors, 3 vectors, A dot B, it results in just a scalar, a real number. Inner products are also linear, so that if I take a ket C and multiply by A, ket B, I'll get CA plus CB. So they're also linear. If I interchange bras and kets, I have to worry about complex conjugation. So BA is equal to AB star. And if vectors are normalized, we can say A times A is equal to 1, just like when we talk in 3-vector space, dealing with unit vectors. If A and B inner product is 0, we say that those vectors are orthogonal. What I'd like to introduce next time will be orthonormal bases, and then we'll move on a little bit more deeply into vector spaces. Thank you.